Welcome to the mini project. So in this mini project, we're going to look at some ways to improve a convolutional neural network in different ways. So the first thing you get to do is choose between two data sets. We're going to have two different sets of images you can choose between. One is humpback whale identification. So looking at whale tails, they're able to identify each humpback whale has a different pattern of blotches on its tail, and it's used to identify different humpback whales. And the other one is X-rays and looking for pneumonia in X-rays images. So you can choose one of those two paths. They both lead to different notebooks. Here's the first notebook with the X-ray images, and here's the notebook with the whales. Here. The notebooks are almost identical except for the images, the data sets. Everything else is almost exactly the same in the two notebooks. So once you've selected one of those, I want you to make a hypothesis of how you can improve this convolutional neural network. So we're going to go through let's go through the notebook and kind of look, and as we go through it, we'll look at some ways of improving the notebook, some things that change. So your job is to make some hypothesis that making this change will improve the accuracy of the results, and then test this out. So let's look at the X-ray notebook here. So as we often do, we load in our standard libraries. We then read in our data from GitHub here. In the X-ray database, we're using a Kaggle database, and similarly in the whale database, we're bringing in data from this Kaggle challenge. Now, the whale database is quite large and takes 7 gigabytes storage, and it takes like 12 hours to run a training on. So I've cut this back down to instead of 600 whales, we're down to the 600 most commonly cited whales and only 10 images of each. So this brings it in a smaller, more manageable data set for us to use for that. Okay, so once we get the data set in here, we display some sample images of them. We set in some callbacks, and again, we don't know much about callbacks yet, but we will later on. Things like this will reduce the learning rate, as if it is not learning, this one will stop the training if learning is not improved here, and this one will just save our network at certain points. We then use an image generator. These files are all the image files are in like JPEG format, and they're stored in the folders over here once we've downloaded them from GitHub. And so we link up this to these folders here. It is also possible to start running these networks on your own computer, installing something called Anaconda, and working on your own version on your own PC. What's nice about that is that you can run it and leave it running for a longer time, often even overnight. And sometimes, especially when we get to larger data sets in the final project, that's helpful. So on some of these here, we will provide links for you to, let me get down here, download this from GitHub into your own PC, and then you can set up a local folder holding those images. And then you'd have to change what data folder is. But by default, it's set up to use the Colab folders here. Okay, so we have an image generator. We can actually do a number of things with this image generator. We could rotate the image. We could randomly shift the or shear or zoom in on the image here. We're just going to be in the X-ray images. We're just going to be horizontally flipping the image left to right here, and that's one thing we have set up. And then we're also going to rescale the image. And again, we always do this for images because we want our values between 0 and 1 rather than 0 and 255. Similarly, with the whale images, we set up, there are some options, but again, we're only rescaling the image values to 0 and 1 here. So one thing you can try is to try to use some image generate or augmentation stuff. So maybe you'd want to do some shifting and stuff. Particularly helpful when we have small image data sets with not that many images, and we're kind of overfitting them. We're not doing well on the we're only doing well on the training data, not the testing data. Sometimes it's helpful to do some image augmentation for that. I do find that somewhat challenging sometimes, but you can try that. And again, with the X-ray image, we are doing horizontal flips, and I'm not even sure if that's a good idea, because maybe the left-right nature of these images, we shouldn't be doing that. So that would be something to try. Okay, then we load in the images from the database with this flow from directory here. We set a batch size here. That's how many images sets we look at before we update the training weights. The larger the batch size, generally the better the performance is. We don't jump around so much. So sometimes people will change the batch size and see how that affects the performance. Also, the image size, we're rescaling the images to 224 by 224 pixels in both of these cases. But you could also, some of the images are quite large, so you could also scale the images only to 512 by 512 or something like that, and see if that were to improve the performance. So you could reset that here. Okay, then we go through and create a custom convolutional neural network. The book goes through, talks about how to do that, and has this code, and this is a description of what it does. We're setting up a 7x7 network. Sorry, my cat's here meowing at me. I don't know if you can hear her, so it's just distracting me a little bit. Okay, so you can set up a initial network that has 7x7 filter as the first filter, and then a max pooling layer, and then a couple other filters. These are 3x3 filters with 128 filter values, and moving on max pooling. So this is one solution here. And again, we just talk about the different layers. Convolutional 2D layers, max pooling layers are the two most common layers that are mixed together here. We can have dropout or spatial dropout layers. Dropout layers tend to be better for our flattened networks or things like that. Spatial dropout layers are a little better for convolutional neural network layers in between these types of convolution 2D layers or max pooling layers. Flatten and dense are, so flatten will convert a 2D layer into a one-dimensional layer, and then dense is our normal standard neural network layer that we've used with the old non-image neural networks. So here we create a custom layout of a network and set that up. It's a little more complicated than the one in the book. The one in the book is relatively short. This is a more complicated version of this. And so we do a number of convolutional layers, max pooling layers, convolutional layers. Now a number of these layers are commented out here. They're in green and have a pound sign before them, and like the spatial dropout layers and stuff. And you could add more layers in here. I often experiment with different layer configurations here, and I often are commenting out or adding in different layers. So this just shows how you can add in some of those here. In the end, we flatten our layer, and then we have just one dense layer with 512 values, and then an output here. So the first thing we do is try this, our own deep neural network structure. And that's in this section 1. And we do that in both. And then in section 2, we look at using a pre-built neural network. So here's section 1. So again, we define our neural network, we train it, and then we print out the results here. And then we try to do same with some pre-trained neural network here. So again, we talk about some of the different pre-trained networks out there. So there's a network called VGG, which was one of the first ones out there, developed in 2014. ResNet, Inception, it was developed by Google in 2014 to 2016, and different combinations of those. are set up. And so here we can create those networks. So here we're using VGG16. And again, this one isn't commented out. So this is one we're using. It's in black instead of green. So VGG16. You can train this on some weights. And so it uses, the weights are all pre-trained with what is called the ImageNet database here. We don't include the top of the network. Instead, we have to customize it to our own network. So once we've got this pre-trained model here, we create a sequential model, and we start with the pre-trained model, and then we add a flattening layer, and then we add a dense layer and an output layer. And this output size has to be targeted to our output. So in the X-ray image one, the output size is 2. In the whale version, there are 200 different whales, so the output size is 200 for this. So let's talk about some things you could change with this. First, let's just talk about the general performance of these networks. So the X-ray image data set is actually a little bit easier. One thing is that you just have to say, predict between two things. Is it pneumonia or not? So right away, even with randomness, you're at 50%. Here, and you can increase that up without, relatively easily. But again, there's some problems with the training data getting quite high while the validation data not improving near as much. And so that's one thing we really want to watch and see if we can get this validation data up better for this. So in the whale database, the accuracy starts very low, and a lot of networks, it's really actually hard to get a network to converge here. That's why I'm using a little more complicated predefined network rather than the one in the book. So you start with rates under 1% with because randomness, 1 out of 200 is not very good. And so you can actually train these up so that it will learn. But again, these networks tend to learn the training data very well, almost memorizing all the whales in the training data, but not validating very well, and so not generalizing very well here. So that's something to watch here. And so you can watch both the training accuracy, and again, it starts off very low, like less than 1% here, and same with validation accuracy, and then slowly builds up for this. Okay, so how can we improve? What are some things we can look at to improve this? Down at the bottom where we describe the write-up in the notebooks, there are some suggestions for this. One is just to try out different pre-trained models here. So we have a number of different pre-trained models that are available for us here, and by default we're using VGG16 here, but you could use one of the other models and just say one of these other models is going to perform better. VGG16 is a little older model. You'd hopefully expect some of these other models to perform a little better, so you could just swap those. When we're using a pre-trained model, we can change if we can train on the weights. So if we're in a pre-trained model and are setting this up here, one of the parameters we can set up here is the model trainable. So we bring in a model with pre-trained weights here, and then we can either set it to false, and then that's the model is fixed. We only will train the top layers we add on to that, or we can set this to true, and it'll adjust the weights on the entire model, fine-tuning them to our image set. So sometimes people find that that's useful to switch this from false to true here. Another thing is that does using pre-trained weights improve the model, or would it be better to use one of these pre-trained models from scratch here? So when we're loading in a pre-trained model like this, we can specify the weights be automatically loaded from pre-trained weights trained on this ImageNet database, but we could also say don't set up the weights at all. Start with random weights, which is what we normally do and train from scratch. Now this would probably take longer to train it, but it might create better results for us to do. So this would be similar. Now, another thing is to look at is if you create your own model, would your own model be as good as one of these like VGG models. So when you create your own model, you start from empty weights, random weights, and so you could look at that. So one of the problems we have again with learning is that both models tend to have much better performance on the training data than the validation data. So sometimes dropouts or spatial dropouts can improve the accuracy of, especially of this, because adding some random noise to this will help. So you could try adding some dropout layers or spatial dropout layers to your network. Now, this is generally you can only generally do this with your custom network. So use your custom network, you can add in some dropout layers or spatial dropout layers in here. And again, some of them are already commented out here. You could also add some at the end here when we're working with the dense layers. You can add some dropouts there. That's helpful. Now, when you're using the pre-built networks, those are already predefined here. And some of them actually have dropout layers built in, and so you can't adjust those. All you can do is adjust the top of the network. And so you can, when you're doing these dense layers here, you could add some dropout layers into that if you wanted. We talked a little bit about adding image augmentation, like horizontal flips or things like that. See if that improve, or some zooming in or zooming out or something like that. You can change the size of the image. We mentioned that earlier. We resize the images to 224 by 224. We could keep them up to 512 or 512. See if that helps. We could add additional layers, dense layers, to our pre-built layers. So it's common sometimes to add some really large dense layers here to do some, or multiple layers, dense layers here. So again, your job is to make an hypothesis here, and then answer these questions. You describe the data set you're going to use. You describe your hypothesis. You test out your hypothesis and run these results. Now, I'll just warn you that these networks can take a little while to train. So when we train these, and they can take a while to train. So let's look like, so this is training for 100 epochs, and it's only taking about 10 seconds for each one with this pre-trained model where we're not adjusting all the weights. And so that whole thing would be done in 1,000 seconds. But in this network, each update takes about 20 seconds, and so 100 updates would take 2,000 seconds. So this is going to take a little longer. So hope you enjoy this.